Fat metabolism is not a passive process. The body doesn't release stored fat because a calorie deficit exists. It releases stored fat because a hormonal signal tells it to. That signal originates from a system of chemical messengers, primarily insulin, cortisol, leptin, and the thyroid hormones, that collectively regulate whether the body is in a storage state or a mobilization state at any given moment. When those signals are functioning at full resolution, the system responds predictably to changes in intake and expenditure. When the signaling slows or becomes less precise, the response changes, not uniformly and not always visibly, but measurably. This is distinct from the question of how much fat someone carries. It's a question of how readily the body accesses what it has stored. Two people with identical body composition and identical caloric conditions can have meaningfully different rates of fat mobilization depending on the current state of their hormonal signaling environment. What the research documents is that this signaling environment changes with age, and that those changes begin earlier and proceed more gradually than most people expect. The standard response to sluggish fat metabolism follows a familiar sequence. Caloric restriction tightens. The reasoning is direct. If the body isn't mobilizing fat efficiently, reduce the available alternative fuel and force the issue. This can work in the short term, but chronic restriction tends to suppress thyroid output and elevate cortisol, two hormonal changes that further reduce the efficiency of fat mobilization. The intervention partially undermines the system it's trying to activate. Cardiovascular exercise increases. Aerobic activity does stimulate fat oxidation during and after exercise, and this remains one of the more reliable levers available. But the hormonal context determines how much fat is made available for that oxidation in the first place. High exercise volume under conditions of elevated cortisol, which often accompanies both chronic restriction and high training loads, can create a hormonal environment that prioritizes muscle catabolism over fat release. Dietary fat is reduced or restructured. Dietary fat is modified on the assumption that dietary fat is either competing with stored fat for oxidation or contributing to the storage problem. The relationship is more nuanced than this framing suggests, and the results of fat reduction interventions in the context of hormonal dysregulation are inconsistent in the literature. What connects these approaches is that they address the inputs to the metabolic system without directly engaging the signaling layer that governs how that system operates. The hormonal signaling relevant to fat metabolism operates through receptor sensitivity, the degree to which target cells respond to a given hormonal signal. Insulin sensitivity, in particular, determines whether cells take up glucose from the bloodstream efficiently or whether glucose remains elevated, suppressing fat mobilization. Leptin sensitivity governs whether the brain accurately reads the body's energy reserves and adjusts hunger and expenditure accordingly. Thyroid hormone sensitivity affects the baseline rate at which cells consume energy. Each of these receptor sensitivities can decline with age, with chronic stress, with disrupted sleep, and with accumulated metabolic load. When they decline, the hormonal signals don't disappear, they simply produce weaker downstream effects. The body may be producing adequate amounts of leptin and experiencing leptin resistance simultaneously. The signal is present, the cellular response has attenuated. This creates a specific kind of metabolic environment, one where the conventional inputs, food reduction, increased exercise, produce smaller than expected hormonal responses because the tissue receiving those signals is less responsive to them than it once was. The research response to receptor sensitivity decline has produced two directions that operate differently from caloric and exercise-based interventions. The first is sleep and cortisol management. The evidence connecting sleep quality to insulin sensitivity, leptin signaling, and fat oxidation is among the more robust in metabolic research. This is not a lifestyle suggestion in the conventional sense. It's a direct intervention on the hormonal signaling layer. The mechanism is specific. Insufficient sleep elevates cortisol and ghrelin, suppresses leptin, and reduces insulin sensitivity within days. Restoring sleep quality reverses those changes on a similar timeline. The second direction involves compounds studied for their effects on cellular metabolic function, including how efficiently cells respond to hormonal input. Research into NAD+ precursors and into compounds that affect mitochondrial activity and cellular signaling pathways has explored whether the downstream cellular environment can be made more responsive to existing hormonal signals. The research is ongoing, and the findings are not uniform, but the mechanistic question being asked is distinct from anything addressed by caloric restriction or exercise volume alone. Within the cellular signaling research space, a category of compounds has emerged that targets the metabolic environment at the cellular level rather than at the level of intake or expenditure. These are not hormonal interventions. They don't introduce or replicate hormones. What the research investigates is whether cellular responsiveness, the efficiency with which cells act on hormonal signals they receive, can be supported through molecular means. NAD+ precursors are among the compounds most studied in this context, given NAD's role in the enzymatic pathways that regulate cellular energy response. The evidence base for this category is still developing. Product quality in the commercial space varies considerably. The distance between what clinical research examines and what consumer products claim is a relevant variable for anyone evaluating this category independently. Hormonal signaling is the governance layer of fat metabolism. It determines not whether stored fat exists, but whether the body is in a state to release it. When that layer operates with reduced resolution through age, stress, disrupted sleep, or accumulated metabolic change, the conventional tools of caloric restriction and exercise work against a system that is less responsive to them. Understanding that distinction reframes what the problem actually is. The question isn't only how much fuel is available, it's whether the system governing access to that fuel is functioning at the same resolution it once did.